and you were getting worried that you had nothing to do, this is something that will keep you busy. And I think almost everyone, many of you have emailed me your project group information. If you haven't, you have to. And I think your project proposals are due sometime in a week or so. And for your project proposal, all I want from you is some information about what you want to work on. It doesn't have to be thoroughly detailed or anything. Some description of the problem that you want to work on. No more than a page. And I'll set it up so that you can submit it on Canvas rather than emailing me. And like I said, no more than a page. It has to tell me what your project is, why it's interesting, and what you want to do. That's all. And if you think that you have some papers that if you already know that you want to read some papers, you can cite them. Any questions about any of this? Homework and projects?
Yes. Homework is due
2 weeks.
2 weeks.
Yeah, every homework is due 2 weeks from when it's due. And when you're submitting homework one, just if you want to share the information about how long it took, do let me know. All right. So let's continue where we left off. At the end in the last lecture, we looked at linear classifiers. We looked at what kind of Boolean functions linear classifiers can express. And then we took a detour. We went to linear regression. And we looked at the standard way of doing linear regression, which is using least squares by minimizing the least square error. And we saw two algorithms for minimizing least square error. One of them is the gradient descent method. The other one is the stochastic version of this. And if you don't remember it, they may look awfully similar to each other, but they have some interesting differences. And we will be looking at stochastic gradient descent for other functions through the semester. So if you have any doubts about that, or if you don't remember it, I encourage you to go back to those slides and take a look at them. Or if you have any questions about them, you can ask now. Yes?
So do we fix the step size?
For now, let's say you fix the step size.
Okay. But
There are actually adaptive algorithms where the step size gets modified as learning proceeds, and it gets smaller and smaller.
it should get smaller and smaller, right? But otherwise you can't convert.
You need a small enough step size. The basic version of the algorithm says it's okay if you have a small enough step size if the sum of it, if their sum goes to, basically there are some properties that need to be satisfied. To prove anything, it needs to get smaller and smaller, and there are many games that you can play with the step size. For the vanilla version, pretend that it's a small one, and maybe by the end of this lecture, or maybe at the beginning of this next lecture, we'll also see again we'll look at step sizes in the perceptron algorithm, and sometime later in the semester we'll look at again we'll come back to stochastic gradient descent for support vector machines, and we'll look at how step size works there, and that's something that you have to keep in mind. Any other questions? Okay, so given that we know everything about linear regression, and by the way, I also mentioned at the end of the last lecture that you can solve least mean square regression analytically. And I did not go over the slide, and I'm not going to do that even now. I encourage you to work through this just to convince yourself that you've understood what's going on. I'm not going to go through this, and this is probably one of those few places where you can actually solve the optimization analytically in this, at least with respect to what's going on in this class. You can solve the optimization analytically, and you can get a solution using basically a matrix inverse. and it's good to work through this. It builds character. But we won't be talking about this. We'll get back to linear classifiers. We've been talking about regression. Let's get back to classification. And classification is this, again, difference being what? What's the difference between regression and classification?
Continuous versus discrete.
Yes, continuous versus discrete. And for most of the semester, we'll be talking about discrete. So let's briefly talk about classification. And classification is interesting because, at least in the binary classification is interesting because many real-world decision problems are classification problems, spam or not spam, or which folder should this email automatically be placed in, or what tags, or which movies should someone watch, and so on. So, over the rest of maybe this month even, we'll be looking at multiple algorithms for linear classifiers. The one that's coming up very soon, probably by the end of today, is the perceptron algorithm, a very old algorithm. And maybe sometime in the next lecture we'll look at another algorithm called Winnow. And these are similar in spirit to the incremental algorithm for least mean squares, in that you are given an example, you do some processing with it, and if there's a mistake, if your current hypothesis makes a mistake, you update, and you throw it away, you take the next example. Another class of algorithms are, you might have heard of this, support vector machines. They are wildly popular, and they come from a more formal analysis of the space of instances, and we'll be working through that after we get through the lectures on computational learning theory. From the probabilistic perspective, there are two famous classifiers. You might have heard of naive Bayes. Naive Bayes is naive in the sense that it makes some rather strong probabilistic assumptions, and it turns out it's also a linear classifier. And the logistic regression is another probabilistic classifier which has a probabilistic intuition, meaning it predicts the probability that the label is a plus or a minus, and yet it turns out it's a linear classifier, and it has some interesting connections to support vector machines. So roughly this will be the sequence in which we'll be looking at linear classifiers. In between, before perceptron, we'll first look at general mistake bound algorithms, and then we'll have this whole session about computational learning theory, and then we'll get to support vector machines. Then we'll get to probabilistic classifiers, which will bring us to naive Bayes and logistic regression. Somewhere around here will probably be in March, mid-March, we'll get to the end of this slide. But let's start off with the first bit, error-driven classification or mistake-driven classification, and see how that works out for linear classification. In all these cases, the prediction, what changes is the learning algorithm. The prediction after learning is done is always the same. You have a weight vector, you're given an input x, you have a weight vector, you take the dot product, you add a bias. If that score is positive, then you predict plus, else you predict minus. In all these cases, it's the same. All these different algorithms may have come from very different sources, different assumptions, but geometrically, they're all the same. Effectively, you're drawing a hyperplane through the space and proclaiming that one side is positive, the other side is negative, in all cases. The game is all about how do you find that hyperplane. Questions about this general lay of the land, and this is just a preview of coming attractions. Yes?
So if there are more than one outcomes, and how do we manage that? So
You mean more than two?
do we provide a range that this
No. The standard way to do that is to break up that decision of more than two into multiple binary decisions. And once we get to the end of this, we will talk about multi-class classification. By the end of this semester, you should be comfortable with binary classification and know how to do multi-class classification. So let's talk about online learning and the perceptron algorithm. So I've split this up into two parts. Before actually getting into the details of the perceptron algorithm, we're going to take for the first time we're going to talk about what does it mean to learn, or how good is your learning algorithm. In particular, there are multiple ways of asking that question. In particular, for now, we'll look at the question of, in the context of the number of mistakes you make while learning. Okay, this gives us algorithms that are called error-driven algorithms or mistake-bound algorithms. Perceptron is an instance of that. So we look at the perceptron algorithm, which learns a weight vector, and we basically go through this proof that derives the mistake bound for the perceptron algorithm. And I'll end at least this chapter with practical tips about what you might actually want to implement. There is the perceptron algorithm for which there's a theorem, and then there's something else that you'll implement, which looks a lot like the idealized version, but to make it work, you need to do a little bit more. So let's start this discussion with of how good your learning algorithm is. Let's talk about quantifying the performance of a learning algorithm. And one way of thinking about this is, how many examples do you need to see? Let's say the examples are coming to you in a stream, in a sequence. How many examples do you need to see before you've decided that the function that you've learned is good enough? What's good enough? To actually answer this question, you need to think about learning protocols. There are different ways in which you can do learning, and so far we've always been looking at supervised learning, but that's not the only one. So I'm going to take a giant detour back to Boolean functions, because these are idealized objects that we can analyze and study and quantify before getting to linear functions. So let's talk about learning conjunctions. Just to recollect what this means, conjunctions are functions, Boolean functions, where you have a collection of Boolean variables, and all of them have to be true for the output to be true. So, in particular, for now, let's consider the case of monotone conjunctions, where all the Boolean variables none of them are negated. There are no negations. So x2 and x3 and x4 and x5 and x100 should be true for f to be true. Let's say this is a function that is hidden from us, and we need to learn. There are many ways of thinking about learning. Many ways in which the teacher and the learner can interact. One protocol, which is active learning, says the following. The learner proposes instances. An assignment from x for all variables from x1 to x100. The learner gives an assignment, and the teacher says, oh, this assignment is positive, or this one is negative, because the teacher has access to this function. And based on this answer, the learner tries to refine its hypothesis. Another protocol is teaching. The teacher, who knows f, directly conveys the function to the learner somehow. Now that's not very clear. We'll look at one example of what this means. The third one, which is the more natural, the most common setting, is supervised learning. There is this entity, a nature, an oracle, or nature, or whatever you want to call it, which randomly samples examples and gives it to the teacher. Now the teacher uses its hidden function to label all of them, and this collection, which is the training set, is given to the learner. The learner does whatever it wants with it and tries to figure out a function that explains the data. So let's look at these. I just want to spend some time on these three. There are other protocols as well, but I just want to spend some time on these three just to point out the differences. This will be probably the only time I'll be talking about active learning. So if you're interested in that, just let's talk about it. So the first protocol is active learning, where the learner proposes instances and the teacher labels them. So let's say the learner knows, in this case let's say you're the learner, and let's say I'm the teacher, and let's say the learner knows that the function is monotone conjunctions. You know the space of functions, and now you can ask, let's say there are 100 this is 100-dimensional Boolean vectors, and you get to ask me, effectively you can ask me, is x100 in the conjunction or not? The way you can ask me that query is by giving me this example. You give me an assignment of all ones except for the 100th one, and you give it to me. And I use my hidden function, which is on top, to find a label. Because x100 is 0, this function, which says that all of these should be 1 for the output to be 1, this function will return 0. So effectively, this is a coded way of asking me, is x100 in the true concept, right?
We cannot decide just on this one. We need another also, all ones, and if it gives 1, then we can decide it's part of it. Because the rest of the ones can also contribute to that 0 output and f100.
This is a monotone conjunction. It's monotone. So if one of these is a 1, there are no negations. So this one query in this particular concept class, in this one query, basically tells you whether x100 is in the answer or not, is in the hidden function or not. What's the next question you'll ask me? 99. You'll set 99 to 0, put all ones, and then I'll tell you that fx is 1 here, which tells you 99 is not relevant. And you'll keep doing this. Go all the way down to 1, and you'll know that x1 is not relevant. At this point, you have all the information. We've exchanged 100 queries, and so what we just invented is a learning algorithm. An active learning that uses active learning to learn this concept. So in a 100-dimensional Boolean space, for the space of monotone conjunctions, the maximum number of queries that a simple algorithm can use is 100. Right? So with 100 examples, even though the space of possible functions is huge, the space of monotone conjunctions is small, so we can learn. Learning is easy in this space under this protocol. Any questions about this particular protocol? Yes?
It doesn't depend on the data.
There is no data, right? We are building this data. The interaction builds the data set. There is no training set. So in this protocol, there is no training set. You start off with an assumption about the function, and then you give me a query, and you get one labeled example. You give me another query, you get another labeled example. Now you are free to choose what kind of queries you want to ask, and in general in active learning, the difficult bit is figuring out what's a good query. Because you want to ask queries that give you maximum information. So think of the following setting. If you have to pay $1 cost for every query, you want to learn the function with minimum cost. That's the game that's usually played in active learning. Now let's look at yes.
We have an idea of what type of feature functions this
Yes.
feature is.
Here, notice that
That's what we
here it's a very strong assumption. Not only do you have an idea about the features, which are the xi's, you also know that the function is a monotone conjunction. If you didn't know it was a monotone conjunction, you have to do a little bit more. In fact, if the function was not monotone, all you need is one positive example that will give you that will give you enough information about which variables are relevant, and then you start eliminating. It's still not terribly hard, and think about it. So, learning conjunctions and disjunctions. Learning conjunctions is not hard. With this kind of active learning protocol. Let's think about teaching. Protocol 2. The teacher wants to convey the function to the learner. So what it does, first the teacher gives the learner one example, a single example that gives all the variables that are in the concept. So it gives this example which has ones only for x2, 3, 4, 5 and x100 and 0 everywhere else, and its label. this gets a label of 1. Is this enough? Have you learned the concept? What could go wrong?
If we assume monotone, then it's done. Otherwise, it's
Is it really done?
other.
You're trusting the teacher too much here.
Yeah.
So, what if the first bit was set to 1 in the example that the teacher provides? Suppose. Did you get the function? In other words, I also need to give, the teacher needs to give counter examples of, to prove that every one of these bits is needed. Yes?
But you said good variables. How good is good?
How good is good? What I mean by good is the variables that are in the conjunction. So this is, I'm just building a protocol here where to show that teaching requires with a sufficiently good teacher and someone who is not adversarial and a learner who is willing to do some work. Teaching requires way fewer examples than active learning. So this labeled example here proves that x2 is needed. This plus the first one proves that x2 is needed because x2 is the only difference between these two things. And by changing x2, the label changes from 0 to 1 to 0. That proves that x2 is needed. The next one proves that x3 is needed. So really, the first bit, the first example there gives a sufficient condition, the rest of them give necessary, and so basically these 6 examples here are necessary and sufficient. Given these 6 examples, a reasonable learning algorithm can figure out the concept and produce the correct conjunction. Make sense? Questions? And feel free to interrupt and ask questions. You guys have gone quiet.
Yes, in college, if it is a conjunction, first example is good enough, right? If you know it's a monotone conjunction.
How do you know that it's good enough? Because just looking at the first example, I don't know whether x2 is really needed or not.
But that's what I meant by good variables. I mean, if I trust it's a good variable.
No, you're trusting the teacher to give the right answer. Unambiguously, this is independent of what the learning algorithm does. So this is the best possible set. Given this training set, you don't need any other information.
So how do
I just wanted to add that it's not good enough because by the first example, we just know for sure that those variables which are 0 are not in the function.
Yes.
But you don't know anything about those variables which are set to 1.
Exactly.
They might be in the function
Or not.
So it's correct but not precise.
That's a very vague statement.
Means like,
It's sufficient but not necessary.
yeah.
What's the name of this learning?
This is something, this doesn't have a name. This is,
The scale of it?
the next slide is going to give you the punchline. This is very difficult. This is assuming collusion between the learner and the teacher.
So if you believe the teacher, why do you think it's just necessary?
This is for the assuming the worst possible teacher. Yes.
So when we have the first condition, we know all the ones out of those ones. There might be some in the conjunction, some are not.
Yes.
So let's say if there are 51, right?
Right.
So we need 50 more examples to figure out, right?
Sure. So the number of examples needed is the size of the conjunction plus 1.
Yeah.
Right? Good. And in the active learning setting, the number of examples needed is the size of the number of variables there. It's not a function of the size of the conjunction. Right. This one is a function of the number of relevant variables. The other one is a function of the number of variables.
So I have a feeling that there's no learning going on. This is like a teaching. The teacher
Yeah,
is giving.
this
the
is not a learning algorithm. This is just some protocol which says this is the best possible data set that you can get. You need at least these 6 examples to learn. And if you had this oracle that produced these 6 examples, it's effectively equivalent to giving the learning algorithm the answer. You can get more examples, but they'll not give you any more information.
So in the previous example with the active learning, you need 100 examples.
You need 100 examples because the learner has no clue what to expect. Whereas the teacher has a clue, knows exactly what the function is, so can directly encode the function in this form. Unfortunately, this is not a very practical algorithm because most often the teachers don't know what they're doing. So let's look at a more realistic situation. So nature provides random examples, the teacher labels them and gives them to the learning algorithm. So let's say this is the data set that you have. Now, I'm not going to make you stare at this and figure out what will happen, but by elimination, looking only at the positive examples, let's say we only look at the ones that are called labeled 1. For all the examples that are labeled 1, you know that the true conjunction isn't present in all of them, right? You know that the variables that are involved in the conjunction are set to 1 in every one of these examples that are labeled 1. Which means you take the intersection of these things and that should give you a good guess for the conjunction. And don't think of this as a learning algorithm or something. This is just a little puzzle. I give you a bunch of examples that are labeled 1, and your job is to figure out what is the minimum set that's needed. Minimum set of variables that will turn the output to 1. And a reasonable way of doing that is to look at all the examples that are labeled 1, find the set that's common to all of them, and that is all you know is a subset of that is required to turn the output to 1. So here you'll get, I just notice that every time the output is 1, x1 is always 1. It just so happens, this is a random set, just so happens that x1 is 1. If this is the only interaction that the learning algorithm has with the true concept, it will end up picking x1 as being part of the hypothesis. With this particular data, we only have an approximation to a true concept. Because the true concept does not have x1, but it just so happens that this slice of data that we looked at always had x1 whenever the output was 1. Assume everything, there is no noise. This is not, so there is no teacher involved here. There is no teaching. Here the oracle only labels randomly drawn examples. And for now, let's pretend that we live in this universe where there is no noise. Because even in those settings, even in this no noise wonderful universe, certain things are just not learnable. So it's good to understand the boundaries. Other questions? In particular, even in this no noise setting, no learning algorithm here would be able to tell using this data that x1 is not part of the true function. So is that a problem? Yes.
It'll probably depend on how often x1 is equal to 0.
Exactly. So that basically gives us a way to analyze learning algorithms. And there are a few ways of doing this, and we'll be looking primarily at two directions. One is to analyze exactly that intuition. If x1 was never 0 on the training data, maybe it won't be 0 too often. Maybe it won't matter. Or rather, maybe it won't show up in cases that will force our concept to make an error. So maybe we are okay. And this, following this line of reasoning, leads us to this framework called back learning, or probably approximately correct learning. And we'll get to that in maybe 10 days or so. Today, we're going to look at something called mistake-driven learning. We update under mistake-driven learning. We update our learning algorithm, our hypothesis every time we make a mistake. So we have a sequence of examples, and the hypothesis, the learning algorithm has done a good job if we don't make too many mistakes during learning. And if we stop making mistakes for a long enough time, we're going to say we are done. We've done a good job. So the number of mistakes made during learning, we're going to use that as a surrogate to quantify how good our learning algorithm is. Mistake-driven learning leads to this idea called online learning. So let's talk about online learning. But before that, any questions about this very vague description of goodness of learning algorithms? Since this is too vague, let's get into some details. Let's talk about online learning. So we'll look at mistake-driven learning, and in particular we are going to look eventually, after a little bit of discussion about mistake-driven learning and some rather purely theoretical algorithms for this, we'll look at two practical algorithms that actually do mistake-driven learning, which are perceptron and Winnow. And somewhere in between this discussion, I'll point out that we can tie all of this back to this idea of gradient descent for a particular objective function. Even though it was originally derived as a mistake-driven learning algorithm, you can also write it as a gradient descent algorithm. Remember gradient descent from least mean squares. There's another objective for which perceptron is gradient descent, actually stochastic gradient descent, which is kind of a nice integration of different lines of approaching this learning problem. What I want you to watch out for through our discussion are issues of like how important is representation. Remember that from our discussion on learning linear algorithms, on linear classifiers last week, a concept that is not classifiable or linearly separable in one space becomes separable if you blow up the feature space. Keep that in the back of your mind. And that question leads to ideas like kernels, and we will talk about kernel perceptron. This is also discussion about features, and throughout the entire semester you have to remember that you never know the feature set. Some of you have been agonizing over the features for the badges game, and I think it's good agony because it helps you realize that out there in the wild you're never going to get the true feature set. So you have to play this game when you actually implement learning algorithms. In this idealized sandbox that we are playing with, we will only have, we'll always assume that we know the true feature space, but very often we don't know the features, so we have to build some, yes?
There's a question. So these three protocols that we saw were different types of online learning?
Which ones? The three protocols? No.
Yeah.
Actually, none of them were online learning. The closest one to online learning is the supervised one. No, supervised. Even in online learning, so I'll talk about online learning. In online learning, the learner does not ever ask questions. It's teacher or nature that keeps providing randomly drawn examples. The difference between the three protocols is to point out that A, the sequence in which you get your labeled examples might make a big difference in how quickly you can learn. So if you want to do any kind of worst case analysis, you cannot make any assumptions about the sequence. So we'll talk about the mistake bound, where you are defining the mistake bound in terms of the worst case sequence. Can I learn even when there is the sequence of examples that comes to me is not optimal, which is the most natural setting that we might end up having.
Okay, so in armor learning, is the learner supposed to get the instances one by one? If we get a batch of instances and then start learning, is it like batch learning or
So
armor learning?
in the literature, if you look at the, let's hold on to that. We'll get to that in a minute. So let's get through some examples, and I'll come to that question. So the motivation for online learning, one way of thinking about it is, say we have a high-dimensional feature space, million dimensions, and suppose the function is very, very sparse. Only a few of them are relevant. Only these 5 variables are relevant. And this is not a toy setting. It shows up a lot, in particular in applications like natural language processing. So you have a sentence, Middle Eastern deserts are known for their sweetness. This is a mistake because it should be desserts. And how do you know this? How do you know that this is a mistake? Because the word sweetness does not show up with the desert with sand. It shows up in the desert with that's sweet. So, but that's a very, very sparse thing. You can have if you have features that are indicators for the number of for every word in the language, that's a huge space, and very, very few of them actually occur. And the true concept, desert versus desert, is a function of a small set of them. So, very often our target functions are really, really, really sparse. So, what we want is the following. We want an algorithm that depends very weakly on the dimensionality of the space and depends instead on the number of relevant attributes. And the question is, how do we represent this hypothesis? The answer, of course, I'm going to get to eventually is we'll use linear classifiers. But the rest of at least the next 20 minutes is sort of a convoluted path through some rather interesting algorithms, which will take us to linear algorithms, linear classifiers. So, what are mistake bound algorithms? Or sometimes they're also called online algorithms. We have an instance space of dimensionality n, and our target is a Boolean function, which is a function in some concept class, and the size of the concept class is, let's say, parameterized by n. This is not an unreasonable assumption. And the learning, yes?
What do you mean parameterized by n? Like as a function of n, or?
So the size of the concept number. So, for example, the number of Boolean functions, the number of monotone conjunctions, the number of arbitrary Boolean functions. It's a function of the size of the input. And the learning protocol that we are going to follow is closer to the third one that we saw. One example is randomly chosen from the instance space. The target function is applied to it, and the learner predicts using its current hypothesis a value, and it compares the value of its prediction to the value of the target, and if they are not the same, then it updates its hypothesis. This is a mistake-driven learning algorithm or an online algorithm. And what we care about is for the learner to make fewer and fewer mistakes as learning goes on. Let's define a mistake. In fact, let's define this quantity, the number of mistakes, for a particular learning algorithm A, given a particular sequence of examples S, and a concept F which is hidden. MA is the number of mistakes this algorithm will make on the sequence. So the algorithm always does this. It's given an example, it checks, it maintains a current hypothesis, it has a way of making a decision on every new example that comes in. And a mistake is simply when this decision does not agree with the oracle. And the number of mistakes the learning algorithm makes on any particular sequence S for a true concept is this MA. We're going to define the mistake bound for a concept space actually. For C, for example, the mistake bound for an arbitrary set of conjunctions or monotone conjunctions to be the worst case. Pick the worst possible function that you can find, f, and the worst possible sequence of examples that show up for this particular function. And let's take the number of mistakes that this algorithm will make on that and call it the mistake bound.
So what is T?
Where is T?
Max over T.
That's max over f. Max over f. So you have a set of monotone conjunctions and you pick for any given conjunction, for any sequence, you can count the number of mistakes the algorithm will make. Okay? And this MA of C is a property of the concept class. What is the maximum number of mistakes that can possibly be made for any function on this in this concept class for any sequence of examples?
Since it defines the hypothesis with the mistakes, and whenever it makes a mistake, then it's very prone to overfit very quickly, right?
It might overfit. Yes. Why might? Because we are still in this idealized setting of no noise.
Okay, we are still in the domain of monotone conjunctions.
No, we are in the domain of functions with no noise. There are standard techniques to convert from online to batch, from online to guaranteeing that you'll do well enough on future. And we'll get to one of those techniques at the end of this chapter, which is called voting. Basically, you keep track of every hypothesis that you looked at, and all of them together vote at the end. And we'll get to that at the end. But for now, let's assume that we are in this idealized setting of no noise, and you have the true feature space. Then there's no overfitting. No? Why?
Because the overfitting is not just about noise. I mean, you are providing a limited sequence, a finite sequence. If this one does not contain any good example, then your function, your learner might overfit.
If this one does not...
Like for example, if x1 is not the target function, but in the sequence, you always have x1 with the value of 1,
Right.
and the hypothesis will consider x1 is the target function.
Right.
But
Sure.
that is an overfit.
That's not exactly overfitting. That's, if anything, underfitting.
Yeah, it's kind of a superset.
You're maintaining a superset of possible things, and you've not made any mistakes on the trade. But keep that thought in mind, and we'll get to this question about converting from mistake bound to a pack bound once we talk about pack. There are standard ways of going from one to the other. But let's talk about, I'm going to define this concept of a mistake bound algorithm the following way. A learning algorithm A is called a mistake bound algorithm for a particular concept class is if this quantity MA of C, the number of mistakes it might actually ever possibly make on any sequence for any function, is a polynomial in the size of the input. Is a polynomial in the complexity parameter here, which is n. What's n? N is the dimensionality. This is the definition.
So we have a closed form solution for this, right?
We don't have, no, no, what do you mean?
So we are saying that mistakes are a function of n, which is a polynomial.
Right, if you are able to prove it. If you are able to prove it, then it's a mistake bound algorithm.
Okay.
It's polynomial or it's O of a polynomial.
Yeah, but means kind of we have a closed form solution.
If you are able to, yes.
So the dimensionality of the instance space is something, and the size of the sequence in one is another thing. how we kind of...
We have not considered the size of the sequence here at all. Right? You don't care about how many examples you have. And in fact, the perceptron algorithm fits this definition. The perceptron algorithm will stop making mistakes after a certain point, irrespective of how big your data set is. And we'll step through the proof that actually gets through this, where you can show this.
So I assume if we are going to find a kind of provide a formula for MA of C, we might kind of try to find some probability relations between size of F, size of S, and kind of these things. So how we find that if MA of C is polynomial, or how?
Good question. Let's look at some algorithms. But before that, I just want to point out this is not the most general setting for online learning, or this is not the most general way of thinking about online learning. There are other metrics, like the mistake bound. There are other metrics. One of them is called regret, which talks about how much loss you would encounter if, after having seen the entire sequence, you go back and you get to see the sequence again, and you have the idealized predictor. How much worse off will you be because you have seen this particular sequence? And there are regret bound algorithms and such things. But we won't be talking about that for now, because this is simpler and it's easier to fit things on one slide. But already we have some interesting points. First of all, why is this interesting? Why is this model of learning even interesting? It naturally shows up in many cases. So let's say you have a robot in an assembly line, and you don't want to go around collecting data up front, train the robot, and then let it run later on. Every time it sees an example, it gets to make a prediction, and then it can update its hypothesis as it goes along, and this assembly line keeps flowing. So as the robot sees more examples, it gets better. It makes fewer and fewer mistakes.
So is it getting feedback from some kind of teacher telling it?
Yes, there is an oracle that the standard setting is the example comes in, the learning algorithm uses its current hypothesis to make a prediction, and then the teacher or an oracle or something gives the true label. And now it gets to compare and update its hypothesis.
How does it update its hypothesis?
Good. That really defines the algorithm, and we'll look at multiple ways of doing this. This is just a class of algorithms. Other questions? Another place where this shows up a lot is streaming algorithms, where you just can't fit your data in memory. You have no option but to only handle one example at a time, or maybe a small set. So online learning is a natural paradigm for those kinds of settings. And the goal is really, notice that this is related to the question that you asked. In the mistake bound learning, we want to make as few mistakes as possible as we go along. The real goal is to make few mistakes eventually. Not on the examples that you've seen, but it's related. Because if I'm able to prove, for example, that the number of mistakes is bounded by a certain number, that's a function of the space and all that, and the learning algorithm has made those many mistakes, then you're guaranteed that you'll never make any mistakes in the future. If I put an upper limit on the number of mistakes. And again, perceptron has that property. So the important things to notice, there are no notions of distribution. There is no idea of these kinds of examples are very, very frequent and X1 may never happen. There is no distribution over the data. That's a big difference between the mistake bound and the pack style, where pack assumes that there is some notion of distribution over data. And the other thing to notice is that there's not much memory involved. You don't need too much memory. All you need to do is to be able to fit at least one hypothesis in memory and one example. So that can be a useful property to have. So the big disadvantage actually is that this is too simple. There are some rather simplistic assumptions being made here. In practice, we often have more memory, so we might be able to do things with it. And even though the mistake bound says you will make only these many mistakes over the data, it gives no clue about when these mistakes will happen. It's possible that your hypothesis may go through, let's say the mistake bound is 10. The algorithm is guaranteed to make only 10 mistakes, and you've made 9 mistakes so far, and then you see a million examples without making a mistake. Have you learned the concept or not? You've gone through a million examples without making a mistake. Is that not good enough? So there is that thing that is better handled in the pack model. But the advantage, yes.
Who sets this upper bound?
Who sets it? Very often we have to analytically compute this upper bound. We want to compute MA of C. Given this concept class, this algorithm will make no more than a certain number of mistakes.
This is not for any function, right? Just for conjunction.
Now this is for any function in a particular concept class. The mistake bound is a property of an algorithm and a concept class. Any concept class.
Can you make an example of a concept class?
A concept class can be a set of monotone conjunctions, a set of monotone conjunctions which have only k literals, the set of all disjunctions, or set of
there are some concept classes that you cannot have any algorithm in this set.
the set of Boolean functions, all possible Boolean functions. Because every time you make a prediction, the next thing can contradict your hypothesis. And you have to, this was the thing that we saw earlier, there are 2 power n Boolean functions. So the size of the concept class is so large that even the worst case is not learnable. Was there a question? Yes.
Can the mistake be directly proportional to the data?
What does that mean?
So if the data is huge, then we can make more number of mistakes. So as you told, like there are like millions.
Right, so the number of mistakes may be a function of what's the size of the data. If all your features are Boolean and you have a million dimensional space, how many unique examples can there exist? 2 power a million. So it is effectively a size of the dimensionality. The size of the data is a function of the size of the dimensionality. In the space of, when we are limiting ourselves to the space of Boolean functions. Once you get to real valued functions, things become different. We are still in the domain of finite dimensional spaces, or finite instance spaces. We are not in infinite spaces which involve real numbers yet.
So that is the mistakes that can happen, but how about the algorithm handling those mistakes?
Right, so the algorithm has to do something smart. Let's look at some examples of mistake bound algorithms, and then you can come back to your question, unless there's a simple one.
I just want to ask, when you say that you have to get the minimum for each target function in C, right?
Right.
I'm just confused about between hypothesis and the concept C.
The concept is the space of functions that from which the target is drawn, and we don't have access to the concept class. The hypothesis is our best approximation of the concept space. So the concept space is a set of functions from which f is drawn. The hypothesis space is a set of functions from which the learning algorithm will search for h.
Is it a subset of concept?
We have no way of knowing. So if, let's say this is a space of concept functions, you could be looking inside a small subset, because this is the only subset that we know how to search over. You could be looking outside because we have no clue what's going on. Or we could be looking over a larger set, because sometimes the larger set might be easier to search over, which I'll point out an example. Or you could be looking over something else. So the hypothesis space is something that the learning algorithm has to figure out. For example, in the monotone conjunction case that we saw, the hypothesis space and the concept space were identical. But very often we have no clue what the hypothesis space is. The hypothesis space is defined by the way we define our model. One example of hypothesis space is a set of all linear functions.
So this is learning from scratch. There's one supervised learning and supervised learning.
This is supervised. This is supervised because Over time, you build up a data set.
Yeah, over time.
Yeah,
There is this third type of learning as well.
supervised.
Then why are we looking for target function in C? Why can't we first define our hypothesis?
We have to. In fact, we have to define our hypothesis space.
We have to hypothesis space first, and then we should look.
Right. The mistake bound algorithms that I'm going to first mention right now are going to work under the assumption that the hypothesis space and the target space are the same. The concept space are the same. Even there, we can make some interesting statements. So this is an extremely restricted setup. And even there, certain things are impossible, like arbitrary Boolean functions. So we've spoken about some mistake bound algorithms, but I've just defined a class of algorithms. Who said that there's any element in this class? So let's look at one function, one algorithm, actually two, which are mistake bound algorithms. In particular, the halving algorithm is an interesting one. It's an idealized algorithm which cannot be implemented in practice, but it's a good theoretical construct to study. So, before the halving algorithm, let me talk about. Yes.
Sorry, just completely unrelated thing. You said that in that very extreme settings, some things are not possible to learn.
Yes.
So is this kind of, philosophically, can human be able to learn something in that environment, or it's not possible for the?
Let's look at the computational aspect of things. Let's only look at the computational aspect of things, and after I finish the discussion on halving, we'll come back to that. In particular, my canonical example for all these things is a set of the concept space of all Boolean functions. Simply because there are so many of them, no search can enumerate. That's the problem. So it becomes a computational issue.
So how is this different from reinforcement learning?
In reinforcement learning, the learner gets to pick. It makes an action, and that influences the next example that comes in. Here, the next example that comes in is random.
So the next example is influenced by the previous.
It's not here.
In reinforcement.
It can be, right? I mean, I don't know how much you're comfortable with reinforcement learning, but the agent takes an action and moves to a new position in the state space, and each location of the state space can determine what's the next example that comes in. Whereas here, the examples are drawn at random. There is no control over what's the next example. So let's look at one mistake bound algorithm, one algorithm which is called Quant. It does the following. It starts off by maintaining, at every point, it maintains the set of all functions in the concept space. The hypothesis space and the concept space are identical here. It starts off with a full set of hypothesis space, the hypothesis functions. When a new example comes in, it picks a random function from the current set of functions in play and makes a prediction. If that is wrong, it keeps all those functions that are consistent and then waits for the next example. Okay? It's a rather simple and unrealistic example, learning algorithm. It starts off with a full set of functions and keeps pruning them to keep only those functions that are consistent, and every time it has to make a prediction, it picks a random one from that and makes a prediction. And notice that because these functions are all consistent, picking a random one will predict all the previous examples correctly. So what's the number of mistakes that this can make? First of all, clearly, after making a mistake, you only keep a subset. So Ci plus 1, which is a set of functions in play at I plus 1 time step, is a subset of Ci. Which means size of Ci plus 1 is less than the size of Ci. Which means this algorithm can make at most size of C mistakes. We've gained nothing here if you think about it. If size of C is 2 power 2 power n, this is not a mistake bound algorithm. if size of C is n for monotone conjunctions, this is a mistake bound algorithm.
So we assume all functions are consistent with I-1, or we check at every step?
At every step, you check every function and keep only those functions that are consistent. Now, this is a good algorithm in the sense that it is provably correct. It's a bad algorithm because it has to check every function. It has to keep this whole hypothesis space in mind. Okay? So this is a mistake bound algorithm for the space of conjunctions. Because effectively, this is the elimination algorithm. You keep all those functions. Remember the elimination algorithm we spoke about for monotone conjunctions? This gives you something like that. It keeps all those monotone conjunctions. Given a new example, it only keeps those conjunctions which are correct, which predict this guy correctly. And keeps moving on. But the problem is, the number of mistakes it makes is size of C, which is not good if the if size of C is big. So let's see if we can do better. Let's talk about this other algorithm called the halving algorithm. It also maintains a set of hypotheses at every step. It starts off with all possible functions. C0 is the set of all possible functions, and we will keep constructing a series of these sets just like before, and we'll stop when there's only one thing left in the set, because that function is you cannot prune the set anymore. What we do is, when an example comes in, instead of picking a random one, we predict the majority label. So we have a set of functions, we evaluate all of them on this example, and predict the majority label. And what that means is, so just mathematically, you count how many of these functions in Ci say 1, how many of them say 0, pick whichever one of them is larger. What will happen if there's a mistake? How many of these functions will be wrong if there's a mistake?
At least half. Half plus one.
At least half. So what you do when there's an error, you throw away the functions that disagree. Because you use majority, you get rid of at least half of this concept class at every mistake. Questions about this algorithm?
It seems that it's not possible to always practice this algorithm on certain type of problems.
Oh, this algorithm is just a theoretical construct. In most cases, this is impractical. But even this algorithm lets us, for Boolean functions, this is optimal, and it can basically let us get rid of arbitrary Boolean functions as we can't do anything with arbitrary Boolean functions, because even this algorithm will fail. So the question is, how
different is this from the previous one?
in the previous one you pick a random one.
Yeah, but we are checking for all functions.
You check all, and you don't check all, you just pick one random function from here. This step is different in the previous one. The previous one, you check one random function and see if it makes a mistake. So you may end up pruning the minority in the previous case. Here you always, if you make a mistake, you prune at least half.
First method, you said you pick a function at random and you check it.
Yes.
What if you pick the same function again and again at random? So
No. After, if it makes a mistake,
if it doesn't make a mistake.
oh, you can do that. Sure.
Again, you pick it up and
Yeah. That's,
it can go into an infinite loop.
why would it go into an infinite loop?
No, not an infinite loop, but it might not be polynomial even if function is small.
You might pick the same function again,
Yeah.
but if it doesn't make a mistake,
That is our answer. That's it.
that's okay.
We stop there itself.
We are counting the number of mistakes. We are not counting the number of steps the algorithm will take. Remember that's a big difference. We are only counting the number of mistakes. It can pick the same one. If it's right, we don't care. We only update our hypothesis when there's a mistake. And the game we are playing now is, how many mistakes will this algorithm make? It's log C, and let's work through that. Suppose it makes n mistakes. At the final step, we know that there's only one function left. At the final step, the size of Cn is 1. To get to Cn from Cn minus 1, we have thrown away at least half of the functions. So size of Cn is at least is less than half of Cn minus 1. And the same thing again and again. The size of Cn, which is 1, is less than 1 over is size of C divided by 2 power n. Right? In fact, this is a lot like binary search if you think about it. You keep throwing away half of the search space at each step. And you do some simple algebra here, and you can show that the halving algorithm will make no more than log of the size of C mistakes, just like binary search. Questions? Now let's apply this. First of all, before applying this idea for specific concept spaces, let's talk about a little bit about it. First of all, it's an impractical algorithm. You can't implement it because you have to actually enumerate every concept. So in all but the most trivial spaces, you can't actually implement, you can't enumerate all possible functions. But again, from the theoretical point of view, this is optimal. If the function is Boolean and if this works, then you'll be able to find the answer. In general, there are some other games that you might want to play, which is, for example, instead of considering the majority label, you might want to consider the expected label. You want to consider a label that will give you the least number of expected mistakes in the future, but that only makes the analysis harder, so let's not get into that. Yes?
So basically what I get from things that we're saying is that we are thinking of searching in a space. So the best search that we have, for example, the question is, can we do in log of n? So in that case, if we have a
for Boolean functions, this is the best you can do.
So if we have a search space like the Boolean, we can't do any search.
Basically, exactly. So the number of Boolean functions is 2 power n, and log of that is still exponential. So even with binary search, you can't do anything. Well, you still need an exponential algorithm, which means it's not mistake bound. For simpler functions, conjunctions, like the function that we saw, if you have n variables, what's the number of conjunctions? Or let's say, monotone conjunction. Or let's say, not monotone, let's say arbitrary conjunctions. What's the number of conjunctions that are possible if you have n bits? I hear about 2 different answers. So there is 2 power n, option 1. That was yours. Any other? Why 2 power n? No, but we also have negations involved.
It's just
Okay.
Yeah, these are not monotone conjunctions. These are any kind. Yes?
You said we have negation.
We have negations.
Not monotone.
2 to the power n plus 1.
2 power. So let's write down some of these options. So I have one call for 2 power n. Another call for, did you say 2 power n plus 1 here? Okay. Any others? That is the same as this.
2 power 2n.
2 power 2n.
Right. Yeah.
3 to the n.
3 to the n minus 1. Not n minus 1, minus 1.
Let's take orders and get rid of constants. What's the constant prediction? Okay, let's take votes. How many people say 2 power n? 1. How many say 2 power n plus 1? About 6. n power n.
Actually, it is m power n.
What's m?
M is like number of conventions.
We want the number of conjunctions.
Just put M. M is the answer.
Okay. How many people? I'm going to take this off the list for now. How many people say 2 power 2n? About 2 power 2. How many people say 3 power n? A lot more. The answer is 3 power n because for every bit, every variable can either be in the conjunction or be negated in the conjunction or not be there at all. So there are 3 options for every variable and there are n of them, so 3 times 3 times 3 times 3 times. So the number of conjunctions is 3 power n. That's the size of the concept space. And the log of that is n, which is great because the halving algorithm is a mistake bound algorithm for conjunctions. In fact, the elimination algorithm that we saw, which basically eliminates all these literals, all the inactive literals, the ones that are irrelevant, operates in order of n space times, so that's an instance of this thing. What if I make this search space even smaller? K conjunctions are the set of conjunctions which have at most k literals, at most k attributes. So only k of the variables are in play and you know k. The number of k conjunctions is 2 power k n choose k, which is roughly 2 power k n power k, and the log of that is k log n, which is wonderful. The halving algorithm will work, but it's a question of efficiency. Can we learn this thing efficiently for in exactly these? Is there a real algorithm which doesn't have to enumerate everything that can learn in this space? So that's the real question. Halving algorithm is this idealized construct that can learn by enumerating everything, but the problem is that of efficient learning. So say you want to learn conjunctions. Say the concept class is conjunctions. Should the hypothesis class also be conjunctions? So what is the problem if your hypothesis class is conjunctions? You might end up with this variable like x1 that lingers around and is always there. You may not get the minimum number of concepts that are around. In fact, that's a theorem. If you have a sample of that may not be readable all the way at the end, so I'll read it out. Given a sample of n attributes that's consistent with a conjunctive concept, it's NP hard to find a conjunctive hypothesis that is both consistent and has the minimum number of attributes. Meaning there's no algorithm that will get rid of the x1 from that first example that we saw. It's true for disjunctions also. And to prove this, you need to go work through the set cover problem. And if you're interested, you can work out the proof. If not, you can take this as the truth. It doesn't matter. So what this means is that we cannot learn a concept if we are working with the hypothesis of conjunctions. We cannot learn a conjunctive concept efficiently if we are learning with conjunctive hypothesis. And that brings us back all the way back to linear classifiers. Remember that conjunctions are also linear classifiers. It turns out we can actually do this if we don't live in the space of Boolean functions and go up. If this was our concept class, the set of linear functions is larger. And if we increase the size hypothesis class to a larger search space, amazingly we can actually do better. In a more expressive class, in a larger class of functions, search surprisingly becomes easier. And this may be one of the more counterintuitive things you might have seen. I have a larger search space, and searching through it is easier than searching through the smaller search space. And that's one of the reasons, another reason why linear classifiers are very, very useful. So let me start winding up, because I don't think I can get to the perceptron algorithm. So basically from this entire discussion, what you need to know is what are online algorithms? What's the mistake bound model? What's this general, the general scaffolding of a mistake-driven learning algorithm? You need to understand the halving algorithm and how it partitions the search space and keeps getting rid of more than half, and understand its the complexity in terms of the size of the concept space. And this last point, which is important, even for simple Boolean functions like conjunctions, maybe it's not a good idea to think of them as conjunctions and just live in the space of linear classifiers and work in the space of linear classifiers and learn, because that lets us sidestep computational issues, and it lets us write efficient learning algorithms. This is the first instance where we've seen the size of the concept class as being a complexity parameter. Concepts may be learnable or not depending on whether the size of the concept class is large. When we go to pack bounds, we'll see a similar sort of analysis. The size of the concept class becomes the complexity parameter. And if the size of the concept class is super exponential, we can't do anything. If it's exponential, it might still be doable because there's a log term that comes in. And if it's polynomial, everything's great. Unfortunately, we don't have too many of those. Any questions about this general thing, or general anything that we talked about today? Either everyone's very shy or people are sleepy, but go over the slides, go over the lecture and come back. In the next lecture, we're going to go back to linear classifiers and see how we can actually implement an online mistake-driven learning algorithm for linear classifiers.